All right. Welcome, everyone. Are you happy to be there? Yeah? Pump it up? All right. We'll try to make sure you're still happy tonight. Has everyone cloned the repository yet?
Yes. So just for everyone to be clear, we're in the session about recursion schemes, right?
Yeah.
Okay.
So maybe I can. Can you see the URL? Yeah. All right.
Say it or write it on the board.
Yeah, I can write it on the board. We also set it up a Gitter channel, so it's so if you can join it. We'll be able to ask questions and share code and so on the Gitter channel. Can you all see that? Yeah? All right. Okay. So back to this. So basically you need JVM, the version 8 is okay. If you have the 9, it's okay too. And SBT. We will be working in Scala. So does anyone there do not know the Scala programming language? Yeah, okay. We're here to help. So during the session, if you have any question, please raise your hand. Ask the question out loud, and if somebody else can answer the question, answer first. And if nobody can answer, we'll be answering, right? And of course, if we are still answering a question or busy at the moment, you can ask your question on the Gitter channel, and we get back to it later. All right? So if everybody who hasn't done it yet can clone the repository and launch SBT and issue the update comments while we are going through the introduction slides. It will help us gain some time during for the remaining of the session. All right, so. So today we'll be working with recursion schemes. Does anybody know a little bit about recursion scheme already? Yeah, okay. See, ish. It's cool. So, welcome. We are very happy to welcome you in our cool company, which is Inc. Inc. is a neat company. It's recursive, of course. Our architect, Olivier, and myself, Valentin, will be your trainers for today. Before we begin, I'd like to add a few thanks to Greg Phil and Amenable, who are contributors to the Matryoshka library we'll be using today. And I wouldn't have been able to do this workshop and understand recursion schemes without their kind and patient help. So let's give them a round of applause. All right, so you are the new hires of our company, Inc. We are there today because we have good news and bad news. We have good news because we've got a new, exciting, big project with our main client, Acme Corporation, and they want to build a meta data lake. We'll see what that means shortly. The bad news is we need to be on production tonight. So we have roughly 6 hours to build that data pipeline. Our architects, namely Olivier, has already thought about the project. It works very well on PowerPoint. And we'll just have to implement a few functions, and it should be okay and on production tonight. But first, since you are our new hires, probably you need a little bit of training. So we are there to do this full training week in 1 hour, roughly. So we are building a metadata lake. What does that mean? Our clients have a lot of different data sources with different data structures. And they want to be able to add new data sources to their data pipeline. A data pipeline for people who are not working in data in general is basically a system that can accept incoming data, make sure it conforms to a schema and it's correct in its structure, and then write it on disk in a suitable format for large-scale processing, right? So usually when you build a data pipeline, you know the structures you will be validating. And in the Scala world, you basically write case classes, and you let the compiler infer the validator for you. The problem is our client has roughly 10,000 data structures, and we won't have time to write 10,000 case classes until tonight. So we have to find a better solution. If we want to be able to accept new data sources without writing new code, it means that our pipeline must be configured at runtime by some kind of schema, right? Of course, we'll be managing many formats for data, like JSON, CSV, and so on. We'll write data as Parquet files for Spark processing, or Avro records for Kafka streaming. And so our central concept will be schema, right? So we want to build the whole thing around the notion of schema. Schemas are real cool. You can use them to validate data. You can use them to generate random data for your tests. You can use them as a blueprint to transform data from one format to another, and so on and so forth. And schemas are basically inherently recursive. Inside a schema, you have a smaller schema, you have smaller schemas, and so on. These are composed of smaller schemas, and so on and so forth. So it's a very recursive beast. And data, when you represent it generically, like in JSON or stuff like that, is also recursive. Inside a JSON document, you have a smaller JSON document, and so on. And when you have a recursive data structure, your first reflex is to write a recursive function to process that data. But the problem is explicit recursion. It has many problems. First, you easily have Stack Overflow's errors and stuff like that if you don't control the depth of your recursion. The compiler won't be able to help you when you write a recursive function that returns an int. the compiler cannot distinguish between the recursive calls and the hint results. And so it can't say, tell you, hey, Paul, you should have put a recursive call there, or you should have put a strict result there. So writing recursive code explicitly can be dangerous. And more importantly, when you write a recursive function, you are mixing two concerns. You are mixing the how I traverse my structure with the what I want to do with each of these components, right? So you are writing code that is not reusable. If you have another processing to do on the same data structure, if you write another recursive function, you will need to rewrite the way you traverse your structure once again. And every processing will need you to write your traversal again and again. But we are fortunate enough to have this recursion schemes abstraction. It comes from a paper from 1991, so it's quite new. No, it's quite old. And it does exactly what we need. It decouples how we traverse a recursive structure from what we do with each of the components of it. And it has a very good implementation in Scala in the library called Matryoshka we'll be using today. So recursion schemes are a family of traversals of recursive data structures. We can split this family in three categories. We have folds that take a recursive structure and destroy it to produce a single value. And the simplest known fold is kata. Dually, we have unfolds that take a simple value and build up a recursive structure out of it. And the most simple one is Anna. And we have refold that combine folds and unfold. You start from a simple value, you unfold it to build a recursive structure, and then you fold it to build another simple value, right? And the simplest one is called idle. Everything good so far? Right? All right. So to use recursion schemes, you need three basic ingredients. First, you need a functor that will be called the pattern functor for your structure. Does everyone know what a functor is? All right. If we talk about notions you don't know, just raise your hand and we'll explain them, right?
Yeah, the best thing would be to whether speak up as we go, or just put up the getter that you need help at some point, and we can help you tackle those afterwards. But less questions are when you have it.
Right. So you need a functor, you need a fixed point. We'll see shortly what that means. And you need an algebra or a co-algebra. So we'll define all these terms right now. So first, the pattern functor. So this is a tree. This is really typically how you would write such a structure in Scala. So you have a sealed tree, and then you have two cases. And at least one of these cases contains a recursive reference to the tree type, right? So here our nodes contain two trees, all right? Nothing fancy, everything is easy. And to make a pattern functor for that structure, the idea is just to replace the references to the tree type by a type parameter, right? So now our treef type has one type parameter, A, and the node class does not contain two trees, it contains two A's, right? And the leaf is rather unchanged because it doesn't contain a recursive reference. And it's a functor, so we need to write an instance for a functor for it. But it's quite easy and straightforward. So this is our pattern functor. The problem with pattern functor is that you've made the recursion inside lifted up in the type system, but you've lost the ability to have a single type that can reference all the kinds of trees you can have. For example, if you have a tree that has a depth of 2, the type will be 3 or 3 of something, right? If you have a depth of 1, the type will be 3 of something. And if you have an unbalanced tree, the type will be something really strange that node of 3f of underscore is a subtype of leaf of nothing. It's a complete mess. You've lost the ability to have a single type that can reference all the shapes of your trees, right? So that's when you need a fixed point. A fixed point type, it's just a type that swallows the recursion. The simplest one is called fix. And as you can see, it takes one type parameter, which is a type constructor. It's a type that has a slot, a f of something. And it contains a f of fix of f. So you see, there we have 2 f's. That's where the recursion is swallowed by fix. And now, we can, if we write a little bit more code, we can have a single type that can be able to reference all the shapes of trees we can have. Yes?
But you lost the type parameter directly, whether it's equal to a case class or
I'm sorry.
But you lost the type, the actual primitive type internally to the
Oh, we've lost the A.
Yes.
Yes, that's the point. Actually, the A is fix of 3f. As you see, fix contains a single field, unfix, that is a f of fix of f, right? That means that this f that is inside will in turn contains fix of f, and so on and so forth. All right? Because the a in our 3f of a is only there to be
Mutated.
yeah, not mutated, but it's a slot for you can plug what you want inside of it. When you plug fix of f, you've got all recursive stuff that is collapsed to a simple type fix of f. All right? Because if we go inside a node of fix of f, both branches are fix of f. So if you go inside these, their sub-branches will be fix of f again, and so on. Right? So with the fixed point type, you unify all the internal types. Right? It's you see it will become natural after a while. So we have yep. Okay, so what about the leaves? Good question. As you can see here, we have a type parameter for leaf, but it doesn't appear in the body of the class. So basically, you can put anything for the A on leaf. It won't change anything. It won't change the contents. So you can use that to unify with whatever A you need. Here we need fix of f, so it's okay. We can, every leaf can be a leaf of whatever we want, because the A type doesn't appear inside the body. All right? Okay, so we have a pattern functor, we have a fixed point type, and now we need the real stuff, which are algebras. So algebras are just the blueprints of what we want to do with each node of our tree, each node or leaf, right? Or each component of our data structure. So algebra is simply a function from f of a to a. So it destroys one layer of our structure to build a simple value. When I say simple value, I mean a value that is not of a recursive type, right? And dually, coalgebras is just the same thing with the arrows reversed. So a coalgebra takes an A and builds up one layer of our structure to produce an f of A. All right? Oh yeah, and in this case, the A type is called the carrier of the algebra. So from now on, we'll talk about carrier rather than the type parameter or stuff like that. Okay? So, is it okay so far?
Is that the type of the primitive that, say, the tree would hold? Or is that the...
No, it's not the value of the leaf. That's what you're saying, right?
Yeah.
No,
So,
it's
Go ahead.
it's the value of what you output at the end of the whole traversal. Okay?
It's a placeholder. That's what we call. That's why we call him a carrier. It's a placeholder that will allow you not to take into account the topology of your tree, but to progressively replace it. And this A, as you will see when you compile, this A at each point where you're going to do pattern matching and construct your algebras or co-algebras, this A will represent the output value that you want, not the inside of the tree itself as it is. And as you saw, that's what's a bit confusing. When you're using the pattern functor, when you're creating your pattern functor, you're not going to parameterize in terms of type. This type will not be useful to parameterize the values of the leaf. You're not changing anything around the tree, you're just abstracting the recursion.
Yeah. Good point. All right, so let's see an example of how that works. I've picked Hilo because everything else can be expressed in terms of Hilo. So once you understand how Hilo works, you basically have the gist of how every other scheme will work. So on the bottom of the screen, you have the real definition of the Hilo function. And we'll try to illustrate that with a little diagram. So these purple squares represent our pattern functor. We have the algebras and coalgebras. So an algebra is just an f of a to a. So it's a little square with a triangle to a triangle. And the coalgebra is the dual of that. So it goes from an a and builds an f of a. And so if we look at the definition of Hilo, it takes an algebra and a coalgebra and a value of type A. So it takes a value of type A, an algebra, a coalgebra from A to FA, and an algebra from FB to B. And at the end, it produces a B. So it's just a fancy way to go from A to B while using a recursive structure on the way. So we start from an A. That will be this little yellow square. The first thing we do everybody see the bottom correctly? Yeah? Okay. So we start from an A. The first thing we do, according to the definition, is to call the coalgebra on that A. That will produce an f of A. Since f is a functor, we can map over that functor. And mapping is just almost like picking A's inside the f of A and applying the function we have to them. And the function we apply is this Hilo, partially applied Hilo, right? We recursively apply Hilo inside our functor with the same algebra and coalgebra. So what that does is that it calls the coalgebra on this inside A that builds up an f of A. So we can map over it. We of course map Hilo, which calls the coalgebra that builds up an f of A. So let's say now yeah, you have a question?
Sorry, it's not obvious to me. How can we tell that recursion terminates?
You can't in the general case. You can't.
Yeah, the compiler won't, I would say, unfold, even if it's not exactly right. The compiler will go through the recursion on, I would say, the type level part. In the end, the recursion will always execute at runtime. But you won't be able to know if your recursion itself will stop in definition. But you won't have to. When you're finished with your session, you will see that the recursion is not yours to handle anymore. So you can assume that the conceivers of Matryoshka managed to apply it.
Actually, termination depends on the structure of your functor. And that's exactly the point we've reached. So let's say that, I didn't say that this functor we use is the tree we've defined just before, right? So we have only nodes that can have 2 branches or leaves. So let's say now we have produced a leaf. So it's an f of a that doesn't have any a inside it, right? So our definition of map for the leaf case doesn't do nothing with the function we passed to map, right? It doesn't evaluate it. So let's say it's the case here. So when we call map on that empty f of a, it returns immediately with a b. So now we have an f of b. So when we have an f of b, we can apply the algebra on it, and that will end up unwrapping the f, and we get a b. Okay? But we were still in the process of applying map to this level 1 f of a, and there is still another branch. So again, we apply recursively high-low on the second a inside that node. That calls the coalgebra, produces an f of a, but let's say it's also leaf, so there is nothing in it to apply the high-low on that. So it immediately returns an f of b. We can apply the algebra of it, and we're done. We have mapped high-low on the whole node. We've got two b's, and so we can consider this node, although is now an f of b, because we have finished mapping on it. So we can call the algebra. That will produce a b. And so we now need to finish the map on the root. So again, it picks an a inside, called the coalgebra, ILO, blah, blah, blah. It's a leaf, so map immediately returns a b. So now we can call the algebra, it gives us a b. And so we finished mapping on the root. So now the root is an f of b. We just have to call the algebra on it. And we're done. We have transformed an a into a b. Is that clear for everyone? We can show it again later, but yep.
When you map it, at some point you're applying high-low, and at other times you're applying algebra, and it's not clear to me.
So first, you apply the coalgebra. That gives you a f, so you can map over it. And where you're done, you are still, when you are doing that, you are still evaluating the arguments to that function. So once you're done, you're able to apply the function, right? Yep.
You talked in the justification about avoiding stack overflow. Is this better than not using the recursion scheme in terms of stack count?
It's a little bit more complicated than that, but having stack overflow in that setting depends on the structure of your functor, and also it depends on the fixed point you use. You can have fixed point types that will make sure that are basically stack safe. So, that are lazy in some way and that will avoid putting stuff on the stack repeatedly. And so you won't have Stack Overflow. You can use recursion schemes to process streams, infinite streams of data. You just have to choose the correct fixed point type. In Hilo, though, we didn't need a fixed point. There are a few things to notice there. First, we never built the whole tree in memory. We just, explored a branch until the end, and then destroyed it, and then the next branch, and so on. That has nothing to do with Stack Overflow, but it's worth noting there. But basically, if our coalgebra produced an infinite tree, we would have a Stack Overflow there. But you see, it depends on what your coalgebra does and the structure of your functor. In our case for today, we are working with schemas that are never deep enough to produce Stack Overflows. Right? If it can fit in memory, the depth is basically too small to exceed. It's 1,000 frames by default on the JVM. So if you have a schema of depth 1,000 nodes, you're in big trouble already. So that's not a problem. Yeah.
Yeah, but once again, the thing is that you're not going to be writing the recursion yourself. Most of the time you get a Stack Overflow because you missed something, because you ended up, going too far or calling multiple times when you should have not. This time you're not going to write the recursion, so the only thing that will trigger a Stack Overflow is the depth, not human error. Because you'll see when we start coding, but the thing is that this basically sums up recursions to pattern matching. And when you're pattern matching, you're not, calling anything nested, so you won't have any recursion call yourself. So that limits the possibility of errors that you have, but it won't fix the fact that if the recursion itself needs to go deeper, then you need to have your stack size ready.
Basically, you cannot screw up, but if your data is too deep, or if it's an infinite stream or stuff like that, you might end up having Stack Overflows. But there are also countermeasures in terms of right fixed points and trampolining and stuff like that. Okay?
That was going to be my question. So you're saying, does Matryoshka have trampolining built in?
Not exactly, but you can use, we'll see that later, but you can use a trampoline monad somewhere into the mix to make sure that you won't blow up the stack in some cases that are deep enough to blow the stack. So a few things to notice on that high-low example is that we don't never build the whole tree in memory. We apply the coalgebra starting from the top and going to the bottom. And we apply the algebra starting from the bottom, going back to the top. This is very, very important to keep in mind. And we only had to write two functions, an algebra and a coalgebra, that can only see or care about one layer at a time. This is also very important. That means that when you are writing, for example, your algebra, you are writing a function that will receive as an argument the result of its own application to the level below, right? If I come back, it will be long. Should have made a GIF of that stuff. All right, it will be too long. So basically, your algebra will be called from the bottom to the top, and at each point, it will receive an f of a, and the a inside this f is just the result of the algebra called on the level below, right? So you only care about one layer at a time. And that's also why you need this A parameter to be anything possible, because in the beginning the tree is a fix of 3, for example. So A, your A type is fix of 3. But when you use an algebra, the A type is the result of the algebra from the applied to the level below. Okay? Maybe it's a little abstract, so maybe we should try an example. So I think I'm done with the slides. And so, is everyone okay with the GitHub cloning and the SBT updating, and you've all downloaded half of Maven Central and so on, and the network is buzzing? All right.
Yeah. If anybody didn't update or compile or manage to do anything with SBT, just raise your hand and I go through everyone. Okay.
So, so for the remaining of the session, we have devised the whole thing in 6 parts. And our plan is to have slices of 1 hour each. Maybe some parts need a little bit of explanation, like I did just now. Some others doesn't. And the idea is we start a new exercise at, say, 10 or 11 or something like that. And each hour we stop together and we see where we are, and if we go on to the next exercise or if we need to answer questions and so on. So you can open the project on your favorite text editor. And for each exercise, we have a little README that will basically tell you where the exercise code is. But it should be pretty straightforward. And so now we need to work on the file that is under src main scala 0-prelude.scala. So I can open that real quick. Yep. Yep. Yep.
So you will have all the, thank you. So you will be able to see, that the project is organized with a main source code that is the src main scala directory, and you will have a package solutions. Well, for the sake of the argument, don't look into the package solutions just right now, because otherwise, I mean, you have everything you need to go back home, but I think the goal is to practice here. So the exercises are all in the same package. You've got a package solutions that we will refer ourselves to afterwards. And you've got tests that all covers what you're going to be producing. To be able to run the tests on the solutions, you just have to change the package to lc 2018.solutions. So you will be able to apply the tests to the solutions if you want to see exactly what's going on and how it should work afterwards. But each test right now fail. So everything doesn't work right now. But you have the specs. So you have everything you need to be able to understand what should be done. And we made in the Scala files, in the exercises, quite a few documentation to be able to help you go through the exercises as well. Okay? C'est chez toi ça, je pense. Parce que... Okay.
Okay, so make sure. I'm in the. Oh, I'm in the solution. Sorry. So yeah, the tests are in src test Scala, and if I want, we have no test for the. Yeah, we don't have tests for the very first exercise, but if I wanted to test the solutions for the part number 1, which is the second one, I just have to add the
.solutions.
.solutions, and it will test the solution code. Of course, if I want to test my solution, I just erase that package. All right?
So the goal is
So
that
the idea, if you don't trust our solution, you can test it. The tests are already there.
So the goal is that you don't have to handle Git in any way. You won't have to commit or change branches. Everything is in the master branch. And once you've pulled the repository, you can work and keep your work afterwards if you want. Okay?
And so what you need to do, we have this little to-do function that it designed it so that it compiles, but it throws an error. And basically your job is to replace this to-do with actual code. All right? So let's get started. Every exercise should have comments that that are there to explain what you need to do and introduce a few notions. And so let's get started. Yep. Oh yeah. So to run the test, I'm there in the SBT console, and so effectively I just have to write tests, and it will run the test. And of course, the test won't work because the code is not there yet. And there is no test for the first exercise. If it compiles, it's okay.
As usual, for those who don't know that much SBT, you can always use the tilt just before and launch the test. It will automatically pick up any source change and automatically run the test and compilation for everything that you do. Okay? The project is compatible with ID IntelliJ, so if you want to import it as an SBT project, everything should work out fine. Sometimes, just a disclaimer, sometimes Matryoshka, Scalasi, and ID IntelliJ, they don't like each other, especially ID. We'll tell you that there are some syntactic errors because, well, the incremental compiler didn't pick up all the subtlety.
Never trust IntelliJ for the red squigglies. Always use the real Scala compiler to make sure that your code compiles on it.
On the exercises and the solutions, most of the time IDE will be compatible. We managed to make it work with the implicits and everything like that. So you shouldn't have any red syntax highlighting in the solutions or at the end of the exercises. But some formulations that Matryoshka and Scalasi will accept, IDE won't necessarily, well, understand it. Okay? So if you have an issue, a question or anything, just raise your hand and we'll come. Okay?
Also, after each part, for those who want it, we can take a short break, and then we move on the next part.